Okay, so yeah, power series turns out to be like an infinite polynomial. So here's the end of that screen that we had. Our power series is c sub I x to the I, and I starts at 0. So we're going to start seeing lots of series that start at 0. The reason we had them start at 1 at the beginning was because we were transitioning from sequences, and we like to have I start at 1 for sequences because then it's like, which term is it, right? I equals 1 is the first term, I equals 2 is the second term. And so then we just took that and then transferred that right into series. Now that we're just getting more into series, it's possible for the index to start at a number other than 1. So like 0. So we're defining, or like we talked about, starting our geometric series from 0, and that would mean it would be AR to the I, not AR to the I minus 1 anymore. Okay? So our power series is some coefficient, which can change as I changes, and then x to the I, which then gives like a polynomial, but that a polynomial for like every power of x to infinity. So it just keeps, you have an infinite number of terms. And we wanted to ask the question, when does the series converge, right? So for what values of x does the series converge? So this is review from last time. So we had this example, and we said, all right, we want to know for what values of x the series converges, and so it's a good candidate for the ratio test. And so we did the ratio test, and when we took this limit, we got the limit to be the absolute value of x. Okay? Because as I gets large, that doesn't affect x. So we didn't get a number like we usually do, right? Normally when we would get a number like 2 or 1/2 or whatever, but now x is involved, and x is just x when I gets big. It doesn't, I getting big doesn't affect x. So now our limit in this ratio test is going to be a function of x. But we're still going to use the idea of the ratio test that says that this series will converge absolutely when whatever this value is what? Less than 1. So now we need to figure out for what values of x is that thing less than 1, and then that will be when the series converges. So solving absolute value x less than 1 is the same as saying -1 less than x less than 1. So these are equivalent. So for this particular series, we said that any number between -1 and 1, and any x value between -1 and 1, makes that series converge. And then we said, well, what about -1 and 1? Because when x is -1, what does this limit equal? So when x is -1, this limit is 1, and that's the inconclusive, right? And when x is +1, this limit is 1, and those are the inconclusive cases. So what we do then is we take the -1 and the 1, and we just plug them in for x in the original series, and then we have a problem just like the homework you've been doing. So we plugged in -1, and we got this series, and you can reason that by the alternating series test that's convergent. That meets the criteria for the alternating series test, so it's convergent. And then we plugged x equals 1 in. When we got x equals 1, we got this thing, which is kind of like 1 over j, right? There's 3/4 j, and it's -1, but it's kind of like 1 over j. But all those fractions are actually bigger than all the fractions of 1 over j, which we know diverges, so that by the comparison test, this is going to diverge. Because all those individual terms are greater than the terms of 1 over j. We're making the denominator smaller, right? We're taking 3/4 of j and we're subtracting 1. Both those things make the denominator smaller, making the whole fraction bigger than a series we know diverges. So by the comparison test, it's divergent. All right, so that's where we left off. And so the actual interval of convergence is everything between -1 and 1, like we said, but then also include -1, but don't include 1. Okay, so then with these problems, if you thought about this on a number line, we could graph this. So this is x values. Those are solutions for x. So these are values of x that when put into that series, would make that series converge. Okay, and so then there's something called the radius of convergence. So basically you have this interval which has this midpoint 0, so that's like the center. The center of the interval is 0. And then the radius is 1. So you can think about this kind of like as a circle, right? So there's like this, the center of the interval is 0. And as long as we're inside that circle, this series converges. And so that's the idea of having a radius. So the radius of convergence then is r equals 1. So in some of the Weber questions, they may ask you for the interval of convergence, or they may just ask you for what's the radius of convergence. So you don't have to actually find the interval, you just have to find kind of like what's half the width of the interval. That's the radius. Because you have a center, right? And out from the center, like a circle, you're going out the same distance out from the center. You don't need a circle. When you go into higher dimensions, then it's actually is geometrically it can go in all directions. We still use that language in one dimension. Even though in higher dimensions you actually do get like a neighborhood like this where it can you have convergence in any direction from that. Yeah. No, just this one. No, we got that from solving this one. Yeah, this is just one example. Okay, any other questions? Okay, so another example. So I want you to write that down. I want you to work on that. See how I get going. So we're asking for what values of x again. We're asking what values of x does this series converge? Does this series converge? So write that problem down. I need to look for something on my computer while you're doing this one. So I'm going to take that off the screen in about 20 seconds. Make sure you write that down. And then you're applying the ratio test and trying to figure out for what values of x. Is that the next example? Okay, so check out what I did. Compare. What's that? Someone asked me a question? Okay, so you get 2i plus 1, or if you could use k or j. So this limit is different than the series, so you can use a different variable. You don't have to use k. If you use k, that's fine, but you can use I or j. It's a different limit that you're setting up than the series index. So you can use a different letter. So you should have gotten, here's the key, that in the new denominator you should have gotten 2i plus 3 or 2k plus 3 factorial. Did you get that? See where that comes from? Because you're increasing k, you're increasing whatever you use for this by 1, but then that gets multiplied by 2. So I used I. 2 times I plus 1 means 2i plus 2 plus 1. So it ends up to be 2i plus 3. So there's one potential pitfall. Everyone see why that's what it is? Okay, and then you should also, for the same reason, you actually get x squared. and the top because you get x times 2 times I have I plus 1 plus 1. So that's 2I plus 3, and the bottom is 2I plus 1. So you have 2 more x's in the numerator. Everyone clear on that? Why you get the plus 3 and why you get x squared. Are we good? Okay, so now we're going to evaluate this limit. As I gets really big, so now x, x isn't affected by I, so just pick x to be any number and let I get really, really large. What's the limit? 0. So what's the question? So the question is, for what values of x does this converge? For what values of x does this converge? Yeah, it doesn't matter what x is. This limit is always 0, which is? Yeah, so for what values of x is this limit less than 1? It doesn't matter what x is. You always get the limit of 0, which is less than 1. Conclusion? Yeah, so this will converge no matter what you put in for x, for any value of x. So then what's the quote-unquote radius? Yeah, so the interval is from negative infinity to infinity, and the radius is infinite. So does this logic make sense? This, no matter what you have for x, this limit will always be 0. Pick x to be a trillion. Pick x to be -5. Pick x to be -100. Doesn't matter what you pick for x. That limit will always be 0. And so that limit will always be less than 1, no matter what x you pick. So that thing will converge no matter what x you pick.
So we're doing this, we just leave x alone, and then we choose to make I really large.
That's what the ratio test is. The ratio test is, as I goes to infinity, of a sub I1 over a sub I. So we're doing the same ratio test that we did before. We look at that, right? And this is like, kind of like R, right? It's the multiplier from one term to the next, like R in a geometric series. And we're saying, does that R become less than 1? If it becomes less than 1, this is becoming a convergent geometric series. Okay. So now we have x in the mix. Well, x is a different value than I. So when I gets big, x is still whatever it was before I got big. Okay? Okay, another example. Okay, did you get this far? Do you agree with this? What's the limit then? Now we can ready to take the limit. Let j get big. What does this become? Not 1/2. As j gets big, what's the limit of this? Absolute value of? Not 3/2. Why is it? X just doesn't go to 0, right? It's j going to infinity, not x going to 0. This is 1. This limit is 1. So then what's the whole thing? The limit as j gets big, the whole thing is? No, you guys, nothing happens to the x, guys. X is not affected by j getting big. X plus 3 over 2. That's the limit as j gets large. And what has to happen for this thing to converge? That has to be less than 1. So remember, x is a different thing than j. It doesn't just go away, right? When j gets big, yeah, j over j plus 1, that approaches 1. But then x plus 3 over 2, it's just going to be itself, right? I got to be me. I got to be me. I don't care what j does. I got to be me. X plus 3 over 2. All right? And so how do we solve that? What does that mean if x plus 3 over 2, the absolute value is less than 1, implies that x plus 3 over 2 is less than 1, but it could also be down to negative 1, right? Now we got to solve this. We want x in the middle, right? We want to figure out what's our interval of x. So first step, multiply. It's like an equation, but you have 3 sides, right? So if you multiply by 2, you get negative 2 less than x plus 3 less than 1. Last step, subtract 3, right? So you subtract 3, you get negative 5 to negative 2, right? So these values of x between negative 5 and negative 2. Oh yeah, sorry, you're right. I forgot the 2. You're right. 2 and 2. Sorry, so yeah, so we multiply by 2, you get between negative 2 and positive 2. Then you subtract 3, it's between negative 5 and negative 1. So what are we talking about? All these values of x, what? They make this limit less than 1. And if they make this limit less than 1, then those same x values do what? Make the series converge. You see that? So if x is negative 4.2, that series will converge. But if x is 1.3, which is outside of this, that series will diverge. Okay, so what do we have to do now? We have to check the endpoints, because negative 5 and negative 1 will actually make that thing equal to 1, and that's the inconclusive case. All right, so we'll erase this. So far we got negative 5 to negative 1, right? And so when x equals negative 5, then we'll have a series that's similar to the ones that you've done. That should be j. J equals 1 to infinity of 1 to the j. And this, what did I say? X plus 3. So when negative 5, we're going to get negative 2 to the j. Is that right? All over j times 2 to the j. So now we've got all these things to the j, right? All these things to the j. Negative 2 to the j over 2 to the j is the same as? Yeah, so you can just put those in a ratio to the j, and you would get negative 1 to the j. And then negative 1 to the j times negative 1 to the j is what? Just 1 to the j, right? It's because every time they're both negative, you get positive. Whenever they're both positive, you get positive. So all this stuff just becomes 1. So negative 2 to the j over 2 to the j, you can just make it the ratio negative 2 over 2 all to the j, which is negative 1 to the j. When you multiply that by another negative 1 to the j, You'll always get positive 1. Because they'll either both be negative 1 or they'll both be positive 1. Convergent or divergent? 1 over j is? It's the harmonic series, divergent. Therefore, keep it strictly less than here for this one. We don't want negative 5 because that negative 5 gives us the harmonic series. So negative 1. We'll get the same thing, but this will be negative 1 will give us positive 2 to the j. And now all this, so now what happens? That's 1. We're still got the alternating now. So we got alternating 1 over j. Conclusion? Right? That's our alternating harmonic series, which is convergent. Is the alternating harmonic series absolutely convergent or conditionally convergent? Conditionally. You have to have the alternating because if you don't have the alternating, it's the harmonic series. So just straight up convergence, this is our answer. But if we had to break this down into absolute versus conditional, what? Strictly between negative 5 and negative 1, what do we have? Absolutely convergent because it passed the ratio test, right? But then at that one point, x equals negative 1 would be conditionally convergent. Okay, so what's our center and radius then? So we could, if we put this on number line, center is negative 3, and the radius would be 2. So this is closed here and open. So we have a center of convergence of negative 3. And look, that comes from the fact that what we had, x plus 3 to the j, right? So x plus 3 to the j means the center of that is what makes that 0, right? Negative 3. And then the radius is out to the ends is 2. Right. Yeah, so then that's certainly convergent, right? Add a bunch of zeros, it's going to be convergent. Okay, any questions on this example? Yeah, so when you check those endpoints, then you'll just get a series similar to all the homework you've been doing without the x. It's not a power series anymore. And you'll use all the techniques, you use your toolbox that we've been building up. Anybody ever? Don't hesitate to ask if I lost you somewhere. We're good? Okay, so now we want to talk about representing functions as power series. So recall that the geometric series, if we start from I equals 0, would be a r to the I. And we know that equals a over 1 minus r, as long as r is in the range from negative 1 to 1. So we know that. So what if, let's look at this function, 1 over 1 minus x. So what does that look like? What does that particular function, what does it look like? In this context. Which is? Yeah, doesn't that kind of looks like a over 1 minus r, right? See that? If what? If a were equal to 1 and r were equal to x. Okay, so then can you write 1 over 1 minus x as a series? Thinking of it as, oh, this is the sum of some geometric series where what, a equals 1 and r equals, so what geometric series would that be where a equals 1 and r equals x? Can you write it? So write it in summation notation, and then write it out its meaning, right? Use summation notation to write 1 over 1 minus x, and then write out what it means. Okay, where's Melissa? Melissa M. Did you get the summation notation? A is 1 and R is x. So if it's 1 over 1 minus x, that equals this, right? So what would it be? A equals 1 and R equals x. Just x? 1 times x. See it? So we're writing 1, right. 1 times x to the I. Starting at I equals 0, right? I equals 0, so be, right? Because this is like a r to the I. Where a is 1 and r is x. All right, and then what would that be? What does that mean, Seth? What is that? Okay, almost. What's the first term? X to the 0. It is. And so x to the 0 is not 0, but rather anything to the 0 is 1. So yeah, so you had it, you just missed that first term. So what does this mean? It means using geometric series, we can rewrite this function, 1 over 1 minus x, as a polynomial. But in order to get the function exactly, what would we need to be true about the polynomial? It needs to go on forever, right? You have to keep adding terms forever. But then there's another condition on this too. What else is also true? So let's take a look at it. Let me show you. So here is 1 over 1 minus x. This is 1 over 1 minus x. So what I want to show you is the partial sums, okay? So that's this next line down here, n starting at 0 to capital N. So capital N is going to be like which partial sum I have, right? So here's when n equals 0. That's the first. So the first partial sum is for when little n equals 0, like the starting value is 0, okay? So that's what we get. So that's the first partial sum of this series. It's just function 1, right? So if you're looking at the sum of what you got there, the first partial sum was 1. What's the second partial sum? What's the second partial sum in your series? 1 plus x to the 1, or 1 plus x. That was the second partial sum. So what is that? That's this. So you see right there around x equals 0, that's a good approximation. But as soon as you get away from 0, it's no good anymore. What's the third partial sum? 1 plus x squared. So that's that red graph is the third partial sum. And we're saying, what are we saying? We're saying it should be approximating the blue graph, 1 over 1 minus x. It does for a little bit, around 1 again, or around x equals 0. Okay? Next partial sum, 1 plus x squared plus x cubed. Yeah, right. Right. For for a larger and larger interval around zero, each partial sum does a better job, like farther away from zero, right? So here's the fifth partial sum with the x to the fourth term. Sixth partial sum. Seventh. So you see where it's like black there? So it's like, to our eye, they're indistinguishable. And that indistinguishable region is getting further and further away from x equals 0 as you take more and more partial sums. But look what's happening on the left there. And what about down here? So how are we doing greater than 1 over here? And what about less than negative 1? You see that with each partial sum, it just keeps flipping up and down at negative 1. Why is this? What's going on? Why doesn't this series approximate the graph out here and out here? Somebody knows. Yeah, we're using a geometric series, which only converges, right? So we're doing 1 times x to the I as a geometric series. When does that converge? Yeah, we know that that's like it's a geometric series, so it's only going to converge when x is between negative 1 and 1. That's what we're seeing with the graphs, right? So to the right of 1 and the left of negative 1, this power series is just not, it's it has nothing to do with the 1 over 1 minus x graph. But here in the middle, between negative 1 and 1, the more partial sums we take, so between negative 1 and 1, the more partial sums we take, it does a better and better job in that interval of getting close to the blue graph. The blue graph doing this, right? The blue graph is doing this. Okay, does that make sense? Any questions? So I think right, so what were we doing? We were comparing this function to this function, and we looked at larger and larger partial sums, and larger and larger partial sums did a better and better job approximating 1 over 1 minus x, as long as x was between negative 1 and 1 in that interval of convergence. So this is the idea of writing a non-polynomial function as a polynomial, right? So we're using a polynomial to write some other type of function. This is the idea here. But that other type of function has to look like, right? It has to look like the sum of a geometric series, and then we can do it. Let's try this. So what about x over 2x squared plus 1? So could we use our geometric series to rewrite this as a power series? And how would we do that? So remember our power series looks like? So how would we use our power series? To write x over 2x squared plus 1. Alex, what will we do? Okay, he wants a to be x, and? Okay, making r equal to? Yeah, that's right. Right, so one. Almost? Do you see it? Because 1 plus 2x squared is the same as 1 minus negative 2x squared, right? So we could rewrite this as like x over 1 minus negative 2x squared. And then there's a, and there's r. Okay, another thing we could do is we could just let a be 1, and once we got the power series, at the very end, just multiply by x, right? Just multiply every term by x. Maybe that'd be easier, because then along the way we'd have, it'd be easier to work with. But either way is fine. Later we're going to see that that's what we want to do. We want to start with a equals 1 and wait till we're at the very last step and then multiply the whole thing by x. Because since it's a power series, it's just a sum of terms, you can just multiply each, multiplying the whole thing by x just means multiplying each one by x. Okay, but for now we'll just do it this way. All right, so here's what we're gonna do. So we're gonna do, when we do this, we want to, I think the way that I organize it is really helpful, so I just encourage you to do it the way that I do it. So g of x is equal to and that's going to be equal to sum of, so I goes equals 0. So a times r to the I, right? X times. Okay, now we want to write this as a power series, and a power series has what form? So I'm going to write this. What can I write the form? Right over here. So remember, a power series is ci x to the I. So we want to get this simply as x to a power, right? And then for each power, we want to know what the corresponding coefficient of that power is. So when we have x to the 5th, we want to know what that C5 is. When we have x to the 8th, we want to know what C8 is. So we want to do some changing to this. So what do we really have? We really have, so a product to an exponent means each factor is raised to that exponent, right? So we're going to have x. Let's do the x's first. How many x's to the I do we have? 2. We have, from the inside here, we have x squared to the I, which is x to the 2i, right? And then we also have the negative 2, right? Which is going to be negative 2 to the I. Which means we have x to the 2i plus 1, right? We have 2i number of x's, and then we always have one more x, right? So 2i plus one more x multiplied together. What's that? Can the a value of -2 is it? No a. I don't know what you mean.
There's like the AR to the I. The a value is 2, right? For this.
No, a was x, right? So I'm just simplifying. This is the AR to the I over here, and now I'm just rearranging it.
Oh, okay.
So it's the a and the r are kind of gone now. Okay, so if we're to write that out, so see this, think what? Write it out. See this, think what? So you write out what that means. Really important. You can do that. So hopefully you didn't just copy down what I wrote, that you're able to do that. You should, by now, you should be able to do that. Let I equals 0, you get the first term. Let I equals 1, you get the second term, etc. And then you add them together. Are we good? Okay, so now in web work, they'll often ask you to find such and such power series, and then they'll ask you just for the coefficients, right? Because the power series is this form. And so now, for this problem, they'll say, what's C0? What's C1? What's C2? What's C3, etc. So what is C0? C0 is the coefficient when the power of x is 0, right? Ci x to the I. So what is the coefficient of, so when it's x to the 0 is 1. What's the coefficient when you have x to the 0? Let's not do that one first. Let's do other ones first. So let's do this one first, C1. What's the coefficient of x to the first in this series? What's the coefficient of x to the first? Because it's C1. Where do we have x? So this is telling us the power of x. Where do we have x to the first, and what's its coefficient? Which one is x to the first? Exhibit A, B, C, or D? A. This is x to the first. So they want the coefficient when it's x to the first, which is 1. Okay, so this is the coefficient when we have x squared. X squared. Where do we have x squared? We don't. So what coefficient would we need? 0. Because there is no x squared. We need to make x squared go away to get our series, right? C3 is the coefficient when it's x cubed. -2. C4 is the coefficient when we have x to the fourth. Got to be 0 because there is no x to the fourth. So we need the coefficient of 0 to make x to the fourth go away to get our series, etc. So what was C0 then? C0 is when you have the coefficient x to the 0, or a constant term. 0. There's no constant term. One more, C of 5 would be 4. So this is often, so they'll have you build a series like this, and then they'll ask you just for these coefficients. So just know what that means. The subscript of the coefficient means the coefficient for x to that power. And you may have a bunch missing. So the ones that are missing, those coefficients will be 0.